Okay, so welcome back. Today we're going to be moving on to section 4.7. And you may be saying to yourself, well, what happened to 4.6? Well, if you look in the textbook, 4.6 just basically is the same as 4.5, only talks about how to use a calculator in doing all those things if you want to use what is called a computer algebra system. This would be like, for example, if you have a TI Inspire calculator. But that's not really something we're going to cover in this class. Instead, we're just going to move on to 4.7, which is section called optimization. And we're going back to word problems. So to start us off, there's a worksheet that is posted on Canvas. I'd like you to all go now and finish up the worksheet. There's also a discussion board where in your groups on Canvas, you're going to post the worksheet as a file and discuss, talk about the worksheet, talk about your answers, and respond to each other. So why don't you pause the video now and do that if you have not already. Okay, so welcome back. We're going to be going back to optimization and talking about this, but let's go over this worksheet first. Sort of provide with what at least I've been thinking about with this worksheet, that about just considering these problems with optimization. So if you read the first question, you have a farmer wants to build a rectangular area for animals and has a fixed amount of fencing. When I think about fencing, I'm thinking about, well, that's the perimeter. Around the perimeter, you have that fencing. So my perimeter is fixed. I have a fixed amount of fencing. But the rectangles can look very different. Let's say that this is 5 units, 5 units, and then 3 and 3. So in total here, I'd have 16 units of fencing to work with. So I could do a rectangle like that, or I could do something like, say, a square, where they each have 4 units. Or I could do something where it's skinnier in one dimension, say like 2, 2, 6, and 6. These are all ones that you could have if you're making a rectangular area. As long as they add up to 16, then you're good. So then the farmer, for question number 2, it says the farmer will want to get the largest area for the fixed amount of fencing available, which makes sense. You know, if you're going to buy fencing, you want to have the largest amount of space inside it that you can. Which one of these rectangles that you have drawn will give you the most area, and why? Now, that's going to be based off of the rectangles you drew, and this is more going to be like a question that you're going to have to consider yourself. For mine, I want to say, well, most area, well, we can calculate what the area is, right? It's length times width. So this one, for example, 5 times 3 or 15. This one, 4 times 4 is 16. And this one, 6 times 2 is 12. So in this one, you have the square being the most area. since area is length times width, and we just compared them. Okay. So suppose one of your sides of the area borders a river, and the farmer doesn't want to waste money by fencing in the river. So let's say we have this river, and their area is something like this. They could put a fence there, but let's say the animals are smart enough that they're not going to jump at the river. An analogy I've used before is in Greek mythology, there was a river of fire called the Phlegathon. Let's suppose that you have Apollo's holy cows that was holy to the ancient Greeks, and you're over by the river Phlegathon. They're not going to be stupid enough to jump into the river of fire, so they're going to stay in this area, and you're not going to want to put up that fence. So will this change which rectangle gives the most area, and why? So that's just a question to consider, and we need to just think about it for a second. The square is what we said last time gives us the most area. But now I've removed the side. I still have the same amount of fencing. So where does that fencing go? So we have to sort of think about that as we continue along. We would mathematically like to find which side gives greatest area. Write down the equations you may know about the rectangles without the side removed. So that's just a rectangle as is. Well, the two things that I know most is that area is length times width, and that the perimeter, I just add up the sides, so that's, I have 2 of the lengths and 2 of the widths. So then it says, using this, can you get a formula in terms of just one variable, right? Now I have length times width. I'd rather just have one variable. So I have this perimeter, and I know my perimeter is just a number. It's fixed. So why don't I solve for one of these? Let's say L. 2L is P minus 2W. That is, L is P minus 2W over 2. So just using substitution, we could plug that in, and we have P minus 2W over 2 times W, or P over 2W, which is P over 2 is just a number, the perimeter is fixed, minus 2 over 2W squared, or just W squared. Now, the next question asks, using calculus, how can we find the largest value for area? When I think area, I think maximum. And maximum, so we're going to want the absolute maximum value. So we could do that by looking at, well, what's R? With first derivative test, I take the area and I find its derivative. What do I get? W here is our variable, so it's P over 2 minus 2W. That is defined everywhere. It's a linear function, so I set it equal to 0. So P over 2 equals 2W. That is, W equals P over 4. And you could check that P over 4, it would be helpful here if we had actual numbers. So to give an intuition, let's just say our perimeter is 16. 16 over 4 would be 4. So then we can say our width being 1 versus our width being 5. If we plugged it into the derivative of the area, what will we get? Well, p over 2 now will be 8, so 8 minus 2, positive. 8 minus 2 times 5, so minus 10, is going to be negative. So we do get that 4. So at w equals 4, that area, which is it's just going to be 16 over 2 times 4 minus 4 squared, is maximum. Okay, so we could compute that number if we wanted. That's 8 times 4, which is 32, minus 16, which is 16. Okay, so, but we don't know if that is going to be our absolute maximum. What we have to check is endpoints. Well, our width, we're not going to want negative numbers, so a lower bound on our width would be 0. But that doesn't really make sense, because then think about the picture as you just have a line, and that has no area in it. And then the other picture is our width could be so much that our length is 0, but that's again a line. That is, our width is 8, right? For the one side, because we have that we 2 times the width. There's 2 widths, the width on the left side and the width on the right side. So we could have 8. That would be a fence starting here, going here, and then going back. But then that's going to have length of 0. Again, it's going to be just a line. So those two cases don't even make sense. And this will be, in general, what will happen is whatever our relative extreme value is what the absolute extreme value is. So as it turns out, our width is 4, gives us the maximum area of 16. Now if our width is 4, we did have the equation above where p minus 2w over 2 is our length. Now p was 16, so 16 minus 4 times 2 is 8 over 2 gives us 4 for our length. So, in the case of a rectangle without a side removed, so that was the first one that we had, was these different ones. Over up here, we get that the square is the best possible one we could get, that we can ask for. Okay. How does this process change when the area borders the river? Well, we still have area equals length times width. But now our perimeter has changed, right? If you look at our picture, we have this side, we still have this side, and we have this side, but we do not have the river side, so our perimeter now is going to be, we'll say it's 2 times the width plus the length. And that changes our problem, right? Because before you had that term that was the 2 with the length. But now you don't have a 2 with the length. So that means if we take the perimeter to be 16 again for an example, length is 16 minus 2w. So our area is 16 minus 2w times w, or 16w minus 2w squared. So then if we try to do the same process, take the derivative, we get 16 minus 4w, set it equal to 0 since it's defined everywhere. So then when we solve for this, you get 16 equals 4w, so w equals 4. And you say, well, isn't that the same as last time? But no, it's not, because our length is 16 then minus 8, or 8. So we have a length that is longer. And you could check when w equals 4 our area. If you take a width that is less, you'll get positive. Width that is more, you'll get negative. So this is a maximum area of 16 times 4 minus 2 times 4 quantity squared is going to be, well, that's 16 times 4 is 64, minus 2 times 16 is going to give us an area of 32. Which, notice that not only are the dimensions different, but look, the area is quite significantly larger. It's twice the area. Okay, so that's what optimization looks like, is like what this problem is, where we're just trying to take this word problem, we're trying to somehow maximize or minimize the situation with the formulas. So let's sort of get a feel for that with writing down, well, what did we do? What was the method? First thing was try to understand the situation. And that often includes drawing some sort of picture. Next part is our sort of notation and formula. So come up with some sort of formula that models the situation. So that's like where we talked about perimeter and area. And that would also be where you'd label things like if it gave what our perimeter was, where you would put that is in that step of what is the notation. After coming up with the notation and formula, you solve, and I'll write it as y equals f of x. That is, put it in terms of, so that you have some variable equals an equation of one variable. Like how here we started with that our area is length times width, and we solved for length so that we only had area equals something that is in terms of width. The fourth part is we find the maximums or minimums. And that's with the first derivative test. And then lastly, you find the quantity you need. So for example, on the worksheet, instead of talking about compute compute the area, you had like this number 7 where it says compute the sides that give you the maximum area. So different word problems might ask different things. Are you computing what the dimensions are, or are you computing the area itself? Okay, so now let's put that into practice with one more problem. Suppose you have a box with a square base and an open top that must have a volume of 32,000 cubic centimeters. Find the dimensions that minimizes the amount of material needed. So, if we have a box, this won't be the greatest picture, but we don't want the top, so I'll highlight it. No top. And that's our picture of trying to understand the situation, is that we want to minimize the surface area, right? Minimize the amount of material. That's the surface. But we want to have a particular volume. Now, if we wanted to say what is the volume of a box with a square base? So what it's basically saying is that this base itself down here is a square. So that's going to have side S, so S squared. And then it's going to have some height H. So just from our basic geometry, the dimensions of a sort of like rectangular prism, as they're often called, is length, width, and height multiplied together. So since our length and width are just S, this is S squared H. What other information might we have? Well, we could look at what the surface area is. And it's quite literally, you're adding up the area of the sides. So like, for example, we have this side with area. Well, the bottom, you have S, so it's S, and then times the length will be H. And then you have 4 more sides like that, so that's 4 times SH because you're adding it 4 times. And then you have to add the bottom side, which has area of S squared. So our surface area is what we're trying to minimize. But our volume, which is 32,000, we have there. We could try to solve, right? Because what's our next step? Is we need to solve in some way to get it to be in terms of one variable. So if you take that equation, solve for H, you divide both sides by S squared, and then you can plug this in for H and get that our surface area is 4S times 32,000 divided by S squared plus S squared, or 128,000 over S plus S squared. Okay. So now we can take the derivative, because our next step, right, is maximize or minimize. We're going to use the first derivative test to do that. So our derivative is, well, this is an S to the negative 1 power, so it's going to be negative 128,000 over S squared, and then plus 2S. Now, if we put our critical numbers up here. The only point where it's undefined is when s is equal to 0. But we can throw that one out because that's when the side length down here, right, if I do that in pink, the side length down here is 0. So basically it's a point with just height. So that is not one that really makes sense. So instead, we'll just set this equal to 0 and solve. Okay, so multiply both sides by s squared, you'll get negative 128,000 plus 2s cubed equals 0. So 128,000 equals 2s cubed. That is 64,000 equals s cubed. So s is 40. And we can make our table choosing s equal 30, s equal 50, plugging it into this formula. And what will we get? Well, we'll get a negative value, and we'll get positive. So what does that give us for our critical number of 40? Well, it's going to be a minimum. Now you could check our endpoints, right? The one endpoint is where we get this s being 0, which we already talked about. That would be just this vertical line that makes no sense. But the other endpoint is where when h is 0, so we basically just have a flat box. Well, that has no area, or that has no volume, it just has area. So that one doesn't make sense, meaning 40 as s is our minimum. Now we want to find the dimensions, meaning we want to find the height. So we do 32,000 divided by 40 squared, and we get a height of 20. So in the end, our dimensions will be 40 by 40 by 20. And that's all the examples we're going to do for today. We'll continue this going into next week. And don't forget there is a quiz on Canvas to do today.